So now when we look at protein function, we're going to take this into a slightly different direction. We're definitely going to continue talking about binding of um, O2 to hemoglobin, myoglobin, but we're going to go back to our structure of hemoglobin. So if you look here, this is zoomed in on that central cavity. So I'm going to circle the region of our protein. And here what we're doing is we're looking at a specific molecule known as BPG, or bisphosphoglycerate. BPG, or bisphosphoglycerate, is a significant molecule. What BPG, or bisphosphoglycerate, is going to do is it's going to have, on a atomic or a molecular level, it's going to have a series of charges that coordinate with these uh, positive or partial positive charges within our hemoglobin. Bisphosphoglycerate has a series of negative charges. Now, bisphosphoglycerate with these negative charges is going to coordinate with all these positive charges. These charges are going to basically be stabilized. They're going to stabilize one another. Bisphosphoglycerate is going to insert itself in this central cavity and just kind of sit tight. It's good. It likes to be there. It's fine. Now, what that's going to do is bisphosphoglycerate is going to stabilize one form of the protein. Now, bisphosphoglycerate is capable of binding that central cavity of hemoglobin, and whenever it does so, it decreases hemoglobin's affinity for O2. So BPG is very important because hemoglobin with 2,3-bisphosphoglycerate, commonly known as BPG or bisphosphoglycerate, you're going to see this huge drop off. And you're going to see that hemoglobin's ability to bind O2 is so much less because it's stuck in that T, or the deoxygenated state of our protein. Now, there's another property or phenomenon of hemoglobin that is important for y'all to know about, and that is commonly known as the Bohr effect. Hemoglobin can be regulated by CO2 and protons. So if we look at this structure right here, this structure right here is basically the N-termini of our protein. This, a molecule right there, is carbon dioxide. Now, carbon dioxide can react with the N-termini of our protein and form what's known as a carbamate. And whenever that happens, it also produces a single proton. So that's going to cause the pH of our environment to go down. Now, there's a little bit to unpack here. One thing that takes place is that this CO2, depicted right here, will react with H2O, and the enzyme that catalyzes this reaction is known as carbonic anhydrase. This carbonic anhydrase will produce this molecule H2CO3. That H2CO3 will release a proton, which is going to cause the pH of the environment to go down as well. Now, ultimately, that reaction, what's going to happen is that reaction is going to lead to the formation of these carbamates. So CO2 and singular protons cause the affinity of hemoglobin for O2 to go down. So this phenomenon that I alluded to and showed on the previous slide is known as the Bohr effect, where the pH of the environment is going to influence hemoglobin's ability to bind oxygen. Now, what's significant about this and what's worth noting about this is that the pKa's of ionizable groups involved in the favorable ionic interactions are disrupted. So let's talk about our different states. Our deoxyhemoglobin, or our T state. there are favorable ionic interactions that stabilize the structure of this protein. Now, the protonated form of histidine 146, his 146, remember the structure of histidine, that's that five-membered ring, at the C terminus of the beta-2 subunit forms an ionic interaction with aspartate 94. So this is a positive residue, histidine 146, and a negative residue, aspartate 94. Okay, so when this is protonated and this is deprotonated, you have this favorable ionic interaction. So this interaction right here stabilizes the T state. The ionic interaction stabilizes the proton against dissociation, increasing the pKa of this His 146. So when this interaction is taking place, then this kind of fortifies this proton right here. So whenever that interaction is taking place, well then that gives that proton less of a place to go. Now, contrast that. Oxyhemoglobin, the R state of our protein. Upon binding of O2, the favorable ionic interactions are disrupted. So when O2 binds, this bond right here gets disrupted. Histidine 146 aspartate 94 interaction is disrupted, returning the pKa to their normal values. His 146 is deprotonated in oxyhemoglobin at normal blood pH of 7.4. This to me, this slide right here, this figure right here, is very, very important for understanding the significance of a couple of different things. Now, before we really dig deep into it, I want to bring up a couple of things. There's the myoglobin binding curve. For this, we don't really care about it. So I'm going to scribble this out. Okay, so let's ignore that. Oh, wait, I've got a better idea. There we go. You could use white to white out this myoglobin binding curve. Okay. Now let's take a couple of these proteins and I'm going to basically block this out. And instead I'm going to label these proteins as A, B, and C. Okay. So those are three different proteins, protein A, B, and C. They're all hemoglobin. And what they do is, let's look at this y-axis. Rather than it being fractional saturation, it's percentage. So this is our 0.5. Because what we care about with proteins A, B, and C is the P50. So what O2 concentration is going to get us 50% saturated? Now let's look at A. If you give protein A an O2 concentration of approximately, now I'm drawing a dashed line from 0.5 going down. Well, that would be at about 20. Okay, so 20 torr. If you give protein A an O2 concentration of 20 torr, then that protein will be 50% saturated. Okay? Now, protein B. Well, protein B needs about, I'm going to call it 35 torr. So protein B needs more O2 than protein A to be 50% saturated. Last but not least is protein C. And I'm going to call that about 45 torr. Okay. Now what I want to do is I want to reveal something you already probably saw, and that is the pHs. So this is actually one protein, or the exact same protein, but under different environmental conditions. Protein A is in an environment where the pH is 7.6, B is where it's 7.2, and C is where it's 6.8. So our pH is going down, so our hydrogen ion concentration is going up. Okay, So in a more acidic environment, what does that mean? That means we've got a greater likelihood of a histidine being protonated. So at a lower pH, our protein is more than likely protonated. So high hydrogen ion concentration or a low pH favors the protonation of histidine 146. Protonation of histidine 146 favors the T state. So this right here, we're favoring our T state in protein C. Our T state favors the release of O2. And last but not least, anything that favors the T state lowers the O2 affinity and causes our P50 to go up. Okay, now this is one other thing that I wanted to highlight is if we wanted to compare, let's just say proteins A, B, and C to one another. This is, it's not, this is just kind of important jargon and lingo. How would you describe the line or I'd say the line, the binding curve for protein A compared to B? You could say that B is A shifted to the right. Okay, so I want you to know this, that if a binding curve shifts right, then P50 goes up and O2 affinity goes down. So when P50 goes up, that means you need more O2 to be 50% saturated. So that means your O2 affinity or your affinity for that ligand has gone down. Now, if we were to change this, if the binding curve shifts left, I'll use a different color, left, well then our P50 has gone down and our O2 affinity has gone up. So one of the ways that I always try to think about this is in terms of a physiological perspective. Let's say that you have a hemoglobin that has a P50 of, 60 torr is the P50. P50, 60. From that, you know that your hemoglobin protein needs 60 torr to be 50% saturated. Well, if you live in an environment where the O2 concentration is 40 torr, what do you need? You need your hemoglobin protein to undergo a change where the P50 drops so that you're at least 50% saturated under the environmental conditions in which you live. Now, so think about shifts left, right when it comes to those oxygen binding curves. Histidine 146 is not the only residue responsible for the Bohr effect. The mechanism is similar for other proteins. So basically anything that leads to pH dropping is going to favor the T state. Here we see the same sort of phenomena observed with CO2. We've got a magenta protein, a blue protein, and a purple protein. Our P50, actually that's what I'm going to do. I'm going to compare these. I'm just going to write my P50s for all these proteins. P50, here, here, and here. Of the 7.4, let's call that 25. Now, when the pH is 7.2, but there's no CO2, well, that's this blue line. So I see a shift to the right. So my P50 has gone up, and I'm going to go, and my O2 affinity has gone down. I'm going to call that 30. What's our variable here, right here, or right here? Well, my pH has changed. Now, last but not least, my pH, that is controlled. But then the other variable that I introduce is I introduce CO2. My P, or sorry, my PO2, or my PCO2 for that matter, sorry, is somewhere in the order of 40 torr. My P50 for that protein, that's somewhere on the order of, again, my x-axis isn't really labeled, so I'm going to call that 35 torr, roughly. What this also displays is that, well, these three different proteins in the tissue, since they have lower P50s, their affinity for O2 is all going to be considerably lower. And so what this is showing is that this purple protein in the tissue loses 88% of the O2 it's bound to. It doesn't really want to lose all of that, but inevitably it does because hemoglobin is impacted by both CO2 and and pH of the environment. All right.